Welcome to an introduction to chemistry, brought to you by Parkbench Tutors. For more information about Parkbench Tutors, look us up on Facebook or visit parkbenchtutors.com. We're going to continue our introduction to chemistry by looking at chemical formulas. We'll start by considering oxidation numbers. An oxidation number represents the charge or an apparent charge of an element in a compound. So many atoms can gain or they can lose electrons to form ions. They will have a charge depending on whether they gain an electron or lose an electron. If an atom loses an electron, then it's got more protons, and protons have a positive charge, electrons have a negative charge, so there'll be more positive charges than negative charges. So if you lose an electron, you're left with a positive charge. So it must apply the other way around as well. If you gain an electron, then you end up with more negative charges than positive charges, so you're left with a negative charge on the atom. Let's relate this to Lewis dot configurations, which we've met in the previous podcast. We take something like sodium. The electron configuration is shown there, and the outer energy level is 3s1. In other words, there's one electron at the highest energy level. So how will we show this in Lewis dot? Remember, apart from the outer electrons, the highest energy levels, we show everything else as a kernel. So there we are, the kernel has Na, and then we have the one dot to represent the electron. So our sodium ion then has a single electron, but if we lose it, then we end up with a positive charge, and that represents the sodium ion. So the difference then between the atom and the ion is the ion has got a charge on, but the atom has to be neutral. In other words, the charges balance each other out. So the sodium ion has an oxidation state of 1 plus. Right? The atom has equal numbers of protons and electrons, so its oxidation state is 0. So all elements, by the way, in their elemental state have got oxidation states of 0. And if you look at the periodic table, you can see that it's grouped in particular ways. Now this grouping, particularly grouping things down in the periodic table, has got a reason, and you will see that this affects their oxidation states, affects their valence, affects the way they form compounds. In other words, what we're going to do now is say, okay, let's look at some of these relationships. What can we find out? So let's start off with group 1. That's the group right over on the left hand side of the periodic table, and you can see if we do Lewis dot diagrams, they all end up with one dot, one electron in the outer highest energy level. So we could represent all of those with just that one single dot, with X is the kernel to anything in that group. So yes, there was a pattern there. For each of these, if we lose an electron, then the resulting ion has a positive charge, and that applies to hydrogen and all the alkali metals, and that's in that group. We say that the alkaline metals then in group 1A all have a typical oxidation state of 1 plus. Note that we didn't actually refer to hydrogen there. Hydrogen is a bit of an exception since it also forms hydrides. But however, since it has oxidation state 1 plus, we keep it in group 1A. And you can see there, right on that left hand side is group 1A, hydrogen, lithium, sodium, potassium, rubidium, cesium and francium, going down the group. Now let's look at group 2A. And from that group we have beryllium, magnesium, strontium and calcium, and again we can start by considering the Lewis dot diagrams. We can see here there's got 2 electrons on the outside, so at the highest energy level. So we can write all of these as X for the kernel and then our 2 dots for our 2 electrons. So here then, what happens if they lose the electrons? In other words, let's assume they lose both electrons. The result is you got a positive charge of 2 plus, and that forms group 2A. They're the alkaline earth metals, right? So they have a typical oxidation state of 2 plus. What about going over to the other side of the periodic table? Let's consider the halogens. They're right over, not quite right over, but almost right over on the right hand side. Start with the Lewis dot diagrams. We have fluorine, chlorine, bromine, and iodine, and you can see they've all 7 electrons in that Lewis dot configuration. So the general representation would be X for the kernel and the 7 electrons at the highest of the energy levels. Okay, so what sort of charge are the halogens going to have? So theoretically you've got 2 choices. They can either gain electrons or they can lose electrons. If they gain electrons, they're all going to have the same resulting charge, which will be 1 minus. Now gaining an electron gives an electron configuration that has higher stability, so that's what's going to happen. So halogens going to have a single negative charge, so we can generally write them as X minus. Okay, knowing the number of these electrons in these outer shells, the highest energy levels, that gives us the valence, and it's a clue to the typical oxidation states. Although you must remember there are elements that will show more than one oxidation state. For a neutral compound, the sum of the oxidation states has got to equal 0. Now in polyatomic ions, the algebraic sum of the oxidation numbers has got to equal the charge on the polyatomic ions. We'll see what this means in a minute. So, common oxidation states. You'll notice hydrogen, cesium, lithium, sodium, potassium and silver all in that same group. That's group 1. They all have an oxidation state of 1+. Barium, beryllium, calcium, magnesium, zinc, manganese, zinc all have 2+. If you go to the other side, you'll see our fluoride, chloride, bromide, iodide and hydride. Those all have 1-. Hydride's a bit of an odd one out there. Obviously it's not a halogen. The hydride of course is hydrogen when it has gained an electron. Copper has 2 oxidation states, iron has 2 oxidation states, nickel has 2 oxidation states. Right, so some of these elements then have typically common oxidation states, which can be either 1 or 2 or 2 or 3 or sometimes 2 and 4. And note that, for example, if we take copper, we write copper with a 1 after it or copper with a 2 after it to indicate its oxidation state. Polyatomic ions also have atomic oxidation states. So cyanide, Cn-, hydroxide, OH-, and all the others, nitrate, NO3-, acetate, CH3CO2-, they all have an oxidation state of 1-. We go right to the other side, ammonium, NH4+, or hydronium, H3O+, they have an oxidation state of 1+. So, knowing our oxidation states, then we should be able to write out the formula. So let's try aluminium chloride. The oxidation state of aluminium is 3+, and the oxidation state of chloride is 1-. So how many minuses do we need to balance 3+? Well, we need 3, right? So we're going to have 3 chlorides for each aluminium. So the formula then becomes AlCl3. The formula, what do we mean by formula? Well, if it's an ionic substance, the formula is actually just a representation of the ratio of ions. But if it's a molecule, it actually represents the number of atoms of each element that combine to form the molecule. So let's try aluminium sulfide. Oxidation state for aluminium 3+, sulfide 2-. So in this case, the resulting compound has a sum of oxidation numbers. It's got to be 0, and if we cross multiply, you can see how we can get that. So 2 lots of 3+ for aluminum gives us 6+, 3 lots of 2- for the sulfide gives us 6-. So we've got to have 2 lots of aluminum and 3 lots of sulfide. Formula Al2S3. Hydrogen sulfide. Start with the same way. Sulfide oxidation state 2-. Hydrogen has an oxidation state of 1+. So how many pluses do we need for the 2-? Well, we must need 2 lots of hydrogen for each sulfide, and that will give us a 0 oxidation at the end. So the formula H2S. Calcium carbonate. Calcium has oxidation state 2+. The carbonate's got 2-, so those will balance just as they are. One of each will give us 0 oxidation state. So CaCO3-. calcium nitrate, the oxidation state of calcium is 2+. The oxidation state of nitrate is 1-. So we're going to need 2 lots of nitrate for the calcium. So we'll have a formula of CaNO3 twice. Note the use of parentheses there. Aluminum hydroxide. The oxidation state for aluminum 3+. The oxidation state for hydroxide 1-. 3 minuses to balance that 3+. So we need 3 hydroxides. So we're going to write that as AlOH3. So, when do we use these parentheses? Well, we use them when we've got polyatomic ions. We don't use them for monatomic ions. It's just with polyatomic ions. So hence we write CaCl2, right? So 2 to indicate 2 lots of chloride there. But CaOH2, and we've enclosed the OH part in parentheses because we want to show that we've got 2 hydroxyl ions there. So here are some to try for yourself. If you want, you can stop or pause the podcast at this point, and you can try writing down what you think is the formula for each of those. We've done it for you here. Potassium hydroxide, KOH. Barium sulfate, BaSO4. Silver chloride, AgCl. Silver nitrate, AgNO3. Ammonium nitrate, NH4NO3, magnesium oxide, MgO, barium hydroxide, BaOH twice. You might want to pause again if you're trying to check your answers. Okay, when we write the names, you can see that sometimes we've changed it slightly. So first of all, note when we write these down, we always put the least electronegative element first. Sometimes might say we put the one with a positive charge on first if it's an ion. So we change the suffix for some elements. The suffix means the ending. So for halogens and oxygen we use the ending ide, IDE. So Cl is a chloride, Br is a bromide, O is an oxide, S is a sulfide, F is a fluoride. What happens if we have more than one oxidation state? We'd actually give a clue here early on. Iron, for example, can have 2 oxidation states. It can have an oxidation state of 2+, or it may have an oxidation state of 3+. So you get those 2 possible oxides there, FeO or Fe2O3, and if we wanted to name them, we use the oxidation or indicate the oxidation state of iron. So FeO becomes iron 2 oxide, and Fe2O3 becomes iron 3 oxide, and we put the 2 and the 3 in parentheses there. So here's another dot for you to try naming. Again, pause if you want and try writing the names down for those formulae. And the answers for each of these: Li2CO3 is lithium carbonate, Cu2O copper 1 oxide, Cui2 copper 2 iodide, NO nitrogen 2 oxide, NO2 nitrogen 4 oxide, NH4Cl ammonium chloride, PbNO3 twice, lead 2 nitrate, and CaBr2 calcium bromide. That ends our first session on formulae, brought to you by Parkbench Tutors. Thank you for watching and listening. We wish you success with your studies. For more information about Parkbench Tutors, look us up on Facebook or visit parkbenchtutors.com.